This video is going to cover how to look at Atwood machine problems and how to make some sense of those. We're going to look at the Atwood machines. We're going to look at tensions, forces, and accelerations in the Atwood machines. What is an Atwood machine? Well, an Atwood machine is basically just a pulley. In an Atwood machine, when we're talking about a pulley, we're talking about an extremely lightweight pulley. In fact, we say that we assume it has no mass. And the string attached to it is also extremely lightweight. Like, again, we assume it has no mass. And the pulley itself, that is like the axis and everything, we assume that is frictionless. So it is a theoretical situation with some lightweight string, frictionless pulley, and the pulley itself is weightless. Because later, when we get into some other rotational motion and circular motion, the weight of the pulley itself will actually come into play. So we're just talking about extremely lightweight ones. If we look at our first example, one thing we have to think about with Atwood machines is we're going in a circle and we have some things happening here. For the most part, I'm going to use this what I call system approach formula. But before I get to that, I do want to just analyze what's going on in a basic Atwood machine setup. Because you have two different masses. So we'll say this one is mass 1. I think we all know this is going to have the force of gravity, which is going to be mass 1 times gravity. But then also, it's also going to have some tension, and I'm going to call that F sub t. Now, mass number 2 is also going to have a force of gravity. Its force of gravity is m2 times g, and it also has a force of tension. Now, the thing about the setup with assuming that the string is weightless and assuming that the pulley itself is weightless and frictionless is that the force of tension on each of these is going to be the same. So this force of tension on mass 1 is going to be equal to the force of tension on mass 2 because it's the same piece of string. It's just bent, but it is the same piece of string and there's nothing stopping it from having a different tension on one side or the other. So the tension is the same throughout. And that is the reason why I'm going to go with the system approach formula. Because when you look at these also, you have to decide which way is going to be positive and which way is going to be negative. And because with our math background, we normally assume that the clockwise direction is the negative direction and the counterclockwise direction is the positive direction, I'm going to stick with that. And so if this is my positive direction, well, the force of tension is going opposite of that. So this force of tension is actually a negative number, whereas this force of tension is going the other way. It's going the opposite of the negative, so it is a positive. So these two tensions are going to cancel each other out. And because those two tensions cancel each other out, I'm going to use this systems approach that we're going to talk about. Now, I wanted to include this information because there are going to be times that we're going to have to go back to these free body diagrams and try to determine separately what's going on in mass 1, what's going on in mass 2, and figure out some information there. So we will need this information. But for the most part, we're going to stick with this formula, which is we're just going to look at the whole system altogether. If I start this problem, it says a frictionless pulley is set up as shown. Mass 1 is 10 kilograms. Mass 2 is 5 kilograms. So in other words, my force of gravity on this one is going to be 10 kilograms. So that's 10 times 9.8. So that is 98 newtons. And this one has a force of gravity, which is 5 times 9.8. So that is 49 newtons. Remember that we said this is going to be our positive direction and this is going to be our negative direction. So in other words, we have a positive 98 and a negative 49 because they're both going down in their own direction. So when we do this formula, we have the acceleration is the sum of the forces over the total mass. So the sum of the forces, well, we decided that this one's positive. We had a positive 98 newtons. And we had this one going down the other way in the negative direction. And so it is going in the negative direction. So that's a negative 49 newtons. And our total mass is 10 plus 5. And so now we just have to add those together and see what we come up with. 98 minus 49 is a positive 49. and our total mass is 15 kilograms. We go to our calculator and we divide that out, and we should get 3.26 meters per second squared, and it is going in the counterclockwise direction. Counterclockwise, that's why it's positive. Notice how I didn't talk about tension in there, and other methods will talk about tension, but I think this simplifies it if we just realize those tensions are canceling each other out, so we're not going to worry about them. With that method, then, we should be able to do a similar approach for finding any masses, any various masses. So notice this total mass was 15 kilograms, but the difference between them, do you see how the difference is 5 kilograms? So here I have another one whose difference is 5 kilograms, but their total mass is different. So let's see what happens when we do this. Our total force, so I don't have a diagram here, but maybe I can kind of refer to the one in the margin. Let's say we have 15 kilograms over here, and we have 10 kilograms over here. And so mass times gravity, that's going to be 15 times 9.8, plus the other force, this time it's going in the negative direction, so it's a negative 10 times 9.8. Our total mass altogether is 25 kilograms. When we do that math up on the top, we get the same number as we had just a minute ago. We get 49 newtons up, the same total force as we had here. The difference, though, is the total mass is greater. And because the force is the same, but the mass is greater, that's going to give us a lower acceleration, 1.96 this time, meters per second squared, and still going in the counterclockwise direction. So now on example C, I have another setup, but this time I have a total of 15, which was the same total as I had on example A. But I have a difference much smaller, only 2 kilogram difference. And so again, we'll set up our formula, and our sum of our forces have an 8 over here and a 7 over here. And even if you just think about that, like think about an exaggerated circumstance. Let's say we had a really big one on one side and a really small one on the other side. It's like that small one's not going to slow it down much, is it? But if the two masses are pretty close together, like 8 and 7, then that's going to slow it down because they're almost balanced, right? They're pretty close to being balanced. So it's going to be a much slower system. Okay, let's continue on with our math here. So this time we have 8 kilograms times 9.8, and we have negative 7 kilograms times 9.8. You have our total this time is 15 kilograms again. So in the numerator, this time our difference is only 9.8 newtons, and our denominator still has 15 kilograms. And so this time our acceleration is 0.65 meters per second squared. If you want to put a 3 on that, you could, 0.653. Notice what's going on is we are looking both at the difference of the two sides. That's basically going on in our numerator because one of them is positive, one of them negative. So we're looking at the difference of the two sides, and we're also looking at the total mass at the bottom in the denominator. Those two things, how they relate to each other, is going to determine our acceleration. Okay, this time we are looking at the tension. So in the last problems, we were looking at the acceleration, and I was just using that systems approach. This time, we're looking for the tension, and because we're looking for the tension, I'm going to go back to these free body diagrams I had at the very beginning, which had the force of tension in them, because I need that force of tension now. So let's figure out what's going on here. First of all, notice it is 10 kilograms and 5 kilograms, which earlier we had 10 kilograms and 5 kilograms. And when we did that, we figured out the acceleration was 3.26 repeating. So that acceleration, which we've already done the math for, is the acceleration that we are going to use down here. So let's just go ahead and say somewhere that the acceleration is 3.26 meters per second squared, because again, that is what we found up above, so we know it, so let's use it. Now, let's talk about that free body diagram, this time including the forces of tension. Over on the left, we have our 10 kilograms, and it's going at 9.8 meters per second squared, so that's 98 newtons going down. And we have our force of tension going up. Over on the right, we have 5 kilograms at 9.8 meters per second squared, and so it is a 49 newtons, and it has a force of tension also going up. Remembering that we're going to consider this our positive direction, and we're going to consider this our negative direction. Let's talk about the net forces on mass 1. So I'm going to come over here, and I'm going to call it force net for mass 1. The net force for mass 1 includes the mass 1 times the gravity. That's going down, but it's positive, right? That's our positive direction. That's a positive number. Then we have the tension, which is going in the negative direction, so let's call that one negative minus the force of tension. Those are the two forces acting upon that, and that is supposed to be equal to mass times acceleration, and that's m1 times the acceleration. This problem is asking me to find tension, so I'm going to rewrite this to solve for force of tension because that's what I'm looking for. So let me rewrite this. I'm going to have a negative force of tension over here on the left. I have my M1A on the right, and I'm going to subtract that M1G from the other side and move it over here. Well, that's a negative force of tension. I don't really want the negative force of tension. I want the positive force of tension. So I'm going to multiply everything by -1 basically. And when I do that, that's going to make the M1G the positive value, and it's going to make the M1A the negative value. So now I have an equation that I can use to find the force of tension. And in just a little bit, we'll write something out in the margin to kind of generalize that of when we can use it, okay? But for now, let's finish out this problem. So we're looking for force of tension. That's what we're looking for. I now have an equation that I can use. I could even, do you see how I could factor out an M1? Let me factor out that M1 to make my math even that much simpler, okay? So now what I really have is I have 10 kilograms and I have 9.8, and I'm going to subtract the acceleration, which is 3.26. That was from the previous problem. And then I can just do that math. So that's going to be 10 times 6.54. And I'm going to multiply that out, and I get 65.4 newtons, and that is my force of tension. Okay, remember I said I was going to write some stuff out in the margin. So remember that the force of tension is the same throughout. So force of tension on mass 1, we can call it Ft1, is equal to Ft2. It is the same tension throughout that string. Then, if we are going up, then we could say that F net is equal to the mass times, and I'm going to say the absolute value because I know throughout this video I have not been talking about gravity in terms of negative, and I know some of you have already been thinking about that. Why are we doing this all with positive? But I think it's going to be easier calculations and make more sense if we just stick with the positive values on both the gravity and the acceleration. So anytime you're going up, this is going to be your equation. Whereas anytime you're going down, it's going to be F net is equal to mass times gravity minus acceleration. That is how to think of it without thinking about the signs. Now you can then go back and look at it and maybe analyze it and figure out, well, actually in this case it's supposed to be positive, but then the acceleration is negative, whatever. You can go back and do that if it helps you make sense of it. I'm just going to think of it as going up, we're going to add them together, and going down, we're going to subtract them. Those are some examples of Atwoods that are like basic Atwoods. In other words, it is just two masses on a single pulley, and that's all that's going on.